Structural buckling is one of the most critical failure modes of a structure, where the structure can suddenly collapse under compressive loads. It is a highly nonlinear phenomena, and it is also known as structural instability. In this video, I will show how to analyze structural buckling using the ANSYS finite element analysis package. I will go over some of these examples that you see animated on the screen. So with that, let's get started. Here are some examples of structural buckling. The column buckling is the simplest example to understand. We have a tube or a column which is under compressive loading at the ends, and at a particular value of this compressive loading, the column will start to buckle. Beyond column buckling, we have plate and shell buckling. Shells are simply curved plates like cylinders or aircraft fuselage. Buckling is always a result of either a compressive loading or a local compressive stress. It's obvious in the case of column buckling. The loading is very clear, but it's not very clear how a cylinder mounted at the base here and undergoing a torsional loading on top. This loading causes the cylinder to buckle in this fashion. So let me explain this. This loading on top is a pure torsional loading, and this causes a state of pure shear in the middle of the cylinder, as I've drawn it here. We know from Moore's circle that 45 degrees from this orientation, we will have a state of normal stresses. So we'll have a compressive stress as shown here, and an equal magnitude tensile stress. So this compressive stress causes these wrinkles exactly at 45 degrees from the axis of the cylinder. We have the same situation here in the case of this B-52 in flight. The fuselage is not generating any lift. It's simply hanging from the wings like a cantilever beam. So we know that in a beam, we will have compressive stresses at the bottom in this particular situation, and tensile stresses on top. But if we move towards the middle of the beam close to the neutral axis, we have a state of pure shear. So that's what you see here in the middle of the fuselage. We have this state of pure shear, very similar to this situation here. And because of this downward loading here, we get wrinkles similar to what you see here. In the case of this glider, which is turning at a very steep angle and possibly generating lift at 2 or 3 Gs as it's turning, we know that on top of the wing, there's going to be bending stresses. So these bending stresses are causing skin panels to buckle inward. So this is a simple case of bending stresses on the skin of the glider. One important point to note here is that buckling does not always mean failure of a structure. So in the case of this column, we know that as soon as we get to the critical buckling load, the column will fail and it will not support a compressive load. But in a big structure with, let's say, lots of columns, or in the case of aircraft fuselage here, we have a number of skin panels, and if a few panels buckle, it does not mean failure of a structure. So there is such a thing called post-buckling loading capability, and I'm going to show you how we can evaluate that using ANSYS. Before I dive into ANSYS, I just want to mention a couple of points about real structures. In real structures, the geometry is not perfect. For example, if you look at this tube from one end, you will see a slight amount of bow or sag. This sagging could be due to gravity loads. For example, if this tube is part of a truss structure, due to gravity loads, there's going to be some amount of sagging of this tube. Also, the loading is not perfectly applied. So for instance, in the case of this column under compression, there's going to be some eccentricity, even if it is very slight. There is no such thing as a perfect loading passing exactly through the middle of a a tube, for example. When we design our structures in a CAD package, our geometry is designed perfectly. So it is a tube is perfectly straight. When we get to the drawing part, that's where we mention manufacturing tolerances. But in a real structure, there are going to be manufacturing inaccuracies. Structure is going to be bent slightly. Even that slight amount of bent is going to impact buckling. So generally, in an imperfect structure, buckling is going to happen at a much lower buckling load compared to an ideal perfect structure loaded in a perfect manner. So when we do buckling analysis using finite element analysis methods, we need to capture these imperfections. The second point is, in real materials, the stress strain curves are inelastic, so they look somewhat like this, and it is recommended for buckling analysis to use either a multilinear model or a bilinear model. So this is highly recommended because the structure can, when it is undergoing buckling, it can actually go into yielding combined with buckling. So we need to capture that behavior. Now, these stress strain curves were generated using tensile testing. We can do a compression testing and get similar curves in the third quadrant. But in the absence of that data, we assume that the tensile behavior, the compression behavior, or the compression stress strain curve is going to be similar to the tensile stress strain curve that you see here. So it's a minor point, but just to keep in mind that we are making this assumption when we do buckling analysis. Nonlinear buckling analysis is done in 3 steps. In step 1, we do a linear static unit load analysis. In step 2, we do an eigenvalue buckling analysis, which gives these load multipliers. So if you take the example of a rod here, and the parameters are given down here, the unit load is either 1 Newton or 1 pound or whatever unit you're using. And when we get the load multipliers from the eigenvalue buckling analysis, that load multiplier is multiplied by the unit load, which is 1, to give us a buckling load. So that's the logic behind using a unit load analysis. You can actually use an actual load, and then you will probably get a load factor of something like 2 or 3. So which means that the actual buckling load will be 3 times the applied load. But unit load analysis makes it very clear and intuitive. In step 3, we can either do a force-based nonlinear buckling analysis or a displacement-based. I prefer a displacement-based analysis because it is easier to get convergence. The other important usage of displacement-based analysis is that you can do post-buckling analysis. Step 3 is basically a standalone structural analysis. We do import engineering materials, and you shouldn't use a nonlinear material like a bilinear material model for this analysis. The important point here is that we do import the deformed or buckled shape. Usually mode 1 is used because that's where the structure is going to buckle given a loading condition. And you can vary the scale of that imported deformed model based on manufacturing tolerances or whatever actual imperfections or the magnitude of imperfections you're expecting. A few points to note here. The static analysis that we do here in step 1 can be either linear or non-linear. In fact, if you do a non-linear static analysis using non-linear material model, you will get a more conservative value of these load multipliers. So the eigenvalue buckling analysis can be done on a non-linear model. The other thing is you may be getting load factors with negative values. So if this is the case, you may want to change your loading direction. I say that, but do not change compression to tension, because you will not get any buckling. So if you have a point load at the end of a cantilever beam going downwards and you're getting a negative load factor value, then switch it to upwards and you will get positive values. Let me elaborate the 3 steps in ANSYS. So here I am in ANSYS Workbench. This is the model of a rod. So I'm just going to get into step 1. I'll just walk through the project tree step by step to show you how this model is set up. So the first thing is that you bring in the geometry and define material. I'm defining 2 materials. So there is a linear steel given here, and I have a non-linear version of the same steel material. So in the non-linear version, I am using a bilinear kinematic hardening model. If I just double click here, the yield strength is 420 MPa and the tangent modulus is E by 100. So whatever your linear or your Young's modulus is, divide that by 100 and you get your tangent modulus. This is what I've used based on Euro codes and other engineering codes. So E by 100 is commonly used unless you have a very specific given value. So moving down from that, I have the mesh. This rod is meshed using 3D elements. So these are 3D quadratic elements. Here's the mesh size. Now let's take a look at the boundary conditions. So I'm modeling this as a fixed connection at both ends. So this is going to be subjected to compressive loads with fixed supports at both ends. So at one end, I'm defining a fixed support right here, and on the other end, I'm defining a displacement, remote displacement boundary condition, where I'm constraining this cross section to remain flat as this end is pushed inwards in compression. So I'm letting the z-axis, which is the axis about which this rod is going to be compressed, to be free, and constraining all other degrees of freedom. I'm also defining this force here, and I'm applying a unit load. So this is the unit load method. The material model that I've applied here is linear. So if you take a look at this, this is a linear steel model. The next step is eigenbuckling module, which is connected to the linear structural module. Here I'm looking to get the first 6 modes, and here we have the first mode. So as you can see, there's going to be you will get these modes in pairs for a circular rod in compression, because there's going to be buckling along the y-axis and then an identical mode in the x-axis. The way to read it is, this is the first mode, this is the second mode, and this is the third mode for all practical purposes. So this is the first mode, buckling mode. This is the second buckling mode, and you can see a complete sine wave here. So as I go to the third mode, you can see 2 waves. So as we go to higher modes, the buckling waves are just going to add up. What we are interested in is just the first or fundamental buckling mode, because this is the load at which the structure will collapse. Also note that ANSYS normalizes the maximum displacement to 1 millimeter, or a unit displacement. Essentially, so this displacement does not really matter. This is just a normalized displacement to show how much or how the structure is going to buckle. But what's important is that the maximum number, which is right here in the middle, is 1 millimeter. So this covers step 1 and 2. Moving on to step 3, I'm going to be showing nonlinear buckling analysis using the force-based method and displacement-based method. So the first thing is create a standalone static structural model. I'm just taking the engineering data from my main analysis, so I get the nonlinear structural steel and the linear structural steel model. I will be using the nonlinear structural steel model here for this analysis. The key point to note here is that what I'm importing from here is the deformed model at mode 1. So this is what you specify here. So this is your, so just click on this, you will get your mode 1 and then your scale factor. I'm specifying 15 millimeters. So if you recall, in the linear buckling analysis, you saw the displacements normalized to a unit value, which was 1 millimeter. So this is 15 millimeter. This should be within your manufacturing tolerance value. So this is where this number is coming from. So once I import the displaced model, let me just show you what I've done here. Since this is a nonlinear analysis, I'm going to be using the nonlinear or bilinear kinematic hardening model. Everything else is same. The mesh and the deformed model was imported from the eigenvalue buckling module. And as you can see here, this is not a straight rod. So when you see it from this end, you can see a slight amount of sagging or bowing, which is representing mode 1 buckling. And here are my analysis settings. Take a note of my step size, initial steps, maximum steps. Just make sure to turn the large deflection on. This is very essential for buckling analysis. So once you go through your analysis, the convergence plot sort of looks like this. It may look different in your case, but it's going to have this small zone of non-convergence where bisection might happen. So this is where buckling is happening. And after that, it's just going to continue. But like I said before, in a force-based buckling analysis, you will run into convergence issues, and that is okay. I mean, it will stop converging right after buckling. So that's the point we are looking for. So what I'm actually looking for here is I'm tracking this displacement, the amount of displacement or buckling displacement, and versus the reaction force. So how much force I'm seeing at the end or at the fixed support. So I've created this chart, which I'll just enlarge it, and you can see that this is the buckling displacement, which is what I just showed. It is the lateral displacement of this point versus the reaction force, or the critical buckling load, if you will. So right at this peak, the solution stopped converging. This is not a valid point, but this is the buckling load that I'm getting from a force-based nonlinear analysis. This is about 72% of the linear buckling analysis. So if you recall, in the linear buckling analysis, we were getting 100,000 kilonewtons. This is 7,300 or 730 kilonewtons. Now let me show you the displacement-based analysis. So I'm just going to open this model. So in the displacement based approach, I have the same material, nonlinear material applied. It's identical model coming from the same previous eigenvalue buckling module. So mesh is identical. The only thing that is different here is the remote displacement. So now instead of setting this to the Z component to free, I'm actually going to move it inwards or applying displacement based loading. So there's no force here. Here are the analysis settings. Once again, make sure to turn on the large deflection. The rest of the settings are identical. I usually equate the step end time to the load. So if I'm applying a load of, let's say, 10 newtons or a displacement of 10 millimeters, I set the end time to 10 seconds so that I can track my convergence plot. So here's what it looks like. Now, as you can see, compared to the force-based analysis, I'm getting good convergence. And this happens all the way, even beyond buckling. So this is the benefit of doing displacement-based buckling analysis. So what I'm tracking here is exactly the same thing. I'm tracking the maximum lateral displacement due to buckling in the middle of the rod, which is this value, versus the reaction force at the end. So this chart is simply the lateral displacement on the x-axis versus the reaction force or the buckling load from the fixed end plotted here. So as you can see, in the displacement based analysis, I'm getting similar buckling load, which is about 71% of the linear eigenvalue analysis, and it is very similar to the force-based analysis. This is the point where buckling happens, and as we continue onwards, we get progressively lower buckling load since the rod is bending and it's not able to support additional load to the same capacity. So as you can see, the force is going down with displacement, and this region is what I called post-buckling region. So what you see here after the peak is a post-buckling phenomena. This rod is not going to be able to support any additional load, and let me just show you or summarize everything on a couple of charts. So in this first chart, I have extracted the buckling displacement versus buckling load data from the force-based analysis, the displacement-based nonlinear analysis, and I'm comparing it with the eigenvalue buckling analysis. In the case of eigenbuckling, there is no displacement. This happens instantaneously. The rod is perfectly straight, and then suddenly we undergo buckling. So there is no gradual displacement. It is what we get from the Euler buckling equation, which is shown here. Note that the K value is 0.5 for a fixed support. So the linear eigenvalue buckling analysis can be compared with the Euler buckling formula. In this formula, just note that K value is 0.5 because this is a fixed support at both ends. So for the first mode, I'm getting a buckling load of about 1,000 kilonewtons, which is identical to what I'm getting from the linear buckling analysis. If you look at this chart, the force-based and the displacement-based analysis are identical. So you can see up to this point where the buckling initiates, the two curves are pretty much on top of one another. This value, I would say, is incorrect. I mean, at this point, the solution started to get into convergence issues. So I would read it as 700 kilonewton buckling load right here. So the two analyses will give you identical result, but the displacement based analysis can predict post buckling behavior. As you can see, this chart keeps going. I also did a beam element based buckling analysis, so everything is same except that I've used beam elements, and I'm using displacement based method, so I'm getting identical buckling displacement versus loading chart, as you can see here. So it is different slightly within the bounds of, you know, numerical computation. This chart on the right is identical to this chart. The only difference is here I'm limiting the maximum displacement to a value of 100, but here I'm just going on to see what happens in, you know, after buckling initiates. And I'm also using the beam element model to study the impact of initial imperfection. So if you recall, we had 15 millimeter of bowing of the rod from the axis. So I'm going to reduce it to 10 millimeter, 5 millimeter, 2, and then 1 millimeter. So as I keep going down, I'm making the rod similar to a perfect rod. As you can see here, this was 15 millimeters, and the force based and the displacement based analysis are converging to this, you know, on this curve right here. If we go down in imperfection, this curve gets more steeper and the buckling becomes more sudden. If you look at this curve, which is 1 millimeter initial displacement or imperfection, the buckling happens very suddenly but at a higher load value. But eventually all these curves converge into a single curve. So far what I've shown in this rod example is purely educational. In an actual structural analysis, I will not be tracking this lateral buckling displacement, but rather this displacement here at the end. The reason is this displacement does not mean much. What we are interested in is structural integrity. So this rod may be part of a big structure, or even if it's on its own, what's important is that the distance between the end point here, the fixed point here, and this point is maintained to within a certain tolerance, regardless of how much lateral displacement we are getting here. Somebody might say that this displacement and this displacement is correlated. So in this simple rod example, that is the case. These two might be correlated, but let me clarify this with a better example. So here in this example of B-52 in flight, what's important is that the fuselage maintains its horizontal orientation with respect to the airflow. So what's important is how much the fuselage hanging like a cantilever beam is dropping down at the nose. So I will be tracking this displacement here rather than the lateral buckling or movement of these skin panels here. So I hope this clarifies this point. So back in the rod example, the way I would do this problem is like this. So instead of a unit force, I will be applying a unit displacement. This is in step 1. This unit displacement gives me a reaction force of this magnitude. In step 2, the first buckling load factor is 3.931. So I'm basically multiplying the reaction force with the load multiplier to get my buckling load. And you can see that I'm getting the same value of 1,000 kilonewtons that I was getting in this previous analysis. To generate this chart, I will simply take the displacement at which buckling is happening, which is 3.931 millimeters. This goes on the horizontal axis right here. And on the vertical axis, I'm plotting the reaction force, which is 1,000 kilonewton. So connect these 2 points and we get the slope of the force versus displacement chart for the linear eigenvalue buckling problem. In step 3, I did the nonlinear buckling problem similar to what I've shown here. and this is the chart that I'm getting for the nonlinear case. So once again, I'm getting very close to 700 plus kilonewtons, just slightly above 700 kilonewtons, which is the same result as before. Now the question is, where do we set our design or allowable load for this rod problem? Allowable load meaning when you're designing it, the design load cannot exceed that load. It's not 700 kilonewtons. It has to be some value below that. To answer this question, we have to really look into the broader context of how this rod is used in a structure. So if buckling of this rod can lead to a catastrophic failure of a structure or a system, then we should have sufficient safety margin. So in that case, I might use a load factor of 2. So that means my limit design load will be, or allowable load will be, set at 350 kilonewtons. If this rod is used in a non-critical situation, meaning if the failure of this rod will not lead to significant loss or catastrophic failure, then we can go as high as 600 kilonewtons. Keep in mind that the higher the safety margin is, the more weight we will get. If we are using this in the context of aerospace structures, then the safety margin might be less than 2. So really it depends on a lot of factors. You can use your intuition. There might be design codes that are that might be guiding the limit load of our structure. So we basically have to use our judgment. What this analysis is showing us, just to summarize, the linear eigenvalue buckling analysis is showing that the buckling load is 1000 kilonewtons. The nonlinear analysis is giving us a more realistic value of 700 kilonewtons, and we should be significantly below this failure point. So I'm going to be using this rod example as a template to show how we can solve more complex problems. Moving on to another example, I took this example from this document DNV RP C208. You can find this document online in a PDF form. This is a large steel structure, as you can see from the given dimensions. You can recreate this geometry from these drawings that I'm showing you here. This structure is supported at the base, fixed here, and a 0.01 meter displacement is applied at this end. So this is the loading. So in a complex problem like this, the first thing to do is to look at the minimum principal stress, because the location of the minimum principal stress is where we will get buckling. So in this particular case, it is this region here. 0.01 meter or 10 millimeter displacement at this end generates a force of 76.4 kilonewton at the base. Here are some of the material properties. The tangent modulus for the bilinear model is E by 1000. The first eigen buckling mode gives a value of 6.1478. So whatever my reaction force is, if I multiply this by the load multiplier value of 6.1478, I get the buckling load, which is 470 kilonewtons. The first mode shows this web bending inwards and outwards. So the pre-buckled mode shape can be defined as this web pushed outwards or inwards. In the case of the DNV document, they are taking a value of 19.5 millimeters. This is based on a code that they're using. So we will go by that. And so I'm going to use 19.5 millimeter as my pre-buckled mode shape or geometric imperfection. I will show the buckling results with this deflection outwards. So the number in this case is minus 19.5 millimeters, and a second case where this is inwards, and we will compare the results of both. So here is the result of nonlinear buckling simulation. You can see for the case of minus 19.5 millimeters, this is how the buckled structure looks like, and in the other case, this is how it looks like. So in one case it buckles outwards, and in the other case it buckles inwards. For the minus 19.5 millimeter case, which is, you know, the flange bent outwards, it actually buckles inwards, as you can see here. In this chart, I'm basically comparing the linear buckling analysis with the nonlinear simulation results. So to generate this linear straight line curve, I'm basically taking my 10 millimeter deflection and multiplying this by 6.14. So this is about 60 millimeters. This number goes here. So on the x-axis, we have 60 millimeters, and on the y-axis, I have a buckling force of 470 kilonewtons. So this is based on linear eigen value buckling analysis. In the case of nonlinear buckling analysis, these two cases match very well. So you can see the red curve, which is minus 19.5 millimeters, and the purple dashed curve, which is 19.5 millimeters positive. They match really well. I also have a case of this green curve here, which is generated by using the tangent modulus to be e by 100 instead of e by 1000. So the extra stiffness after yielding results in a curve which is shifted upwards. Another case here is almost identical to the 19.5 millimeter is when I take the initial imperfection to be 12.25 millimeters, which is slightly less than 19.5. Again, there is no difference in the results. So the buckling is really, in this case, is insensitive to the initial geometric imperfection. So now the question is, which value of limit load should we pick? Do we go by a safety factor of 2 or 1.25? So it all depends on the context of this problem. As per DNV C208 document, they are following a code to establish the allowable limit. And if you follow their process, you will see that they are picking a value which is, you know, slightly above 200 kilonewtons. So basically it's right here on this chart. This value is very close to a factor of safety of 2.0. Let me show you this problem in ANSYS. So I'm just going to double click this. I modeled this as a shell structure. So it's going to be meshed with shell elements. Here is the bilinear material model, and I have a linear version of that. This is the mesh size here. The boundary conditions are simple. I have a fixed support at this end and displacement applied at this edge here. As per the DNV document, the displacement is minus 10 millimeters downwards, and I'm not allowing any rotation of this edge or translation in the X or Z directions. The key result here is the minimum principal stress. So as you can see, these blue arrows are pointing inwards towards each other. So this represents the minimum principal stress. And this is where we expect this structure to buckle. Here's the reaction force when a 10 millimeter displacement is applied here. So it's about 76,000 kilonewtons. So in step 2, I performed an eigenvalue buckling analysis. Here is mode 1. So this is how the structure is deforming in mode 1. So to proceed to step 3, I'm basically importing the model with a scale factor of 19.5. So let me open this model here. If you look closely from here, you can see that the model is imported deformed slightly. So this slight amount of deformation is about 19.5 millimeters. The boundary conditions are exactly the same, but instead of 10 millimeters, I'm applying minus 500 millimeters downwards, just to make sure that this model undergoes buckling. The material model is bilinear, and here's a quick look at my analysis settings. Just make sure to turn the large deflection on. Here is the force convergence plot. So at this point right here, the model buckled. So that's why we have a little bit of convergence issue. But note that this is a displacement based analysis. So even after buckling, we get convergence. Here is what I'm tracking. So basically I'm tracking the displacement here in the y direction versus the force. And this is the chart that I showed you earlier. So this is how the structure starts to buckle, exactly at the location where we were getting minimum principal stress. Right at this location. Here's an example of shear buckling. I have this cylindrical shell which is fixed at this end, and I'm applying a remote displacement. I'm basically twisting this edge with respect to this end. So I'm essentially applying a torque on this structure to twist it. Here are the details of the remote displacement that I'm applying. So all components are 0 except for the z-axis, where I'm applying a 1 degree rotation, as you can see here. The key result to see here is the minimum principal stress. So let me just orient it this way. So as you can see, this end is being twisted in this direction, and if I zoom in, I can see the two principal normal stress directions. So this compressive stress, along with the axial stress, which is pulling like this, causes shear wrinkling that I showed earlier, if you recall this phenomena here. So we have a compressive stress and a tensile stress in this direction. So this is causing these wrinkles. So if you look at mode 1, you can see these shear wrinkles. Now, when I did the eigenvalue buckling analysis, I set the negative load multipliers to 0 or no, which means all my load multipliers are positive values. So if you get negative numbers here, you can just change the settings to no here. Note that ANSYS normalizes the maximum displacement to 1, so the actual magnitude that you see here, it does not really matter. Now moving on to the nonlinear analysis, I'm basically going to import the deformed model at a scale factor of 1 and the mode 1. So let me just open this and show what I've done here. So my boundary conditions are identical to the linear analysis. Here's a quick view of my analysis settings for the nonlinear simulation. Once again, note the large deflection is set to on. I'm applying a rotational displacement of 1 degree. 1 degree is sufficient because if you recall, my first load multiplier was something like 0.396 here. So it's less than 1. So 1 degree means I can go into the post-buckling regime. Here's my convergence plot. So it converged without any problems, and in this region we started to get buckling. During buckling, I'm tracking the total deformation, tangential displacement along this edge, along this y-axis, which is the theta axis in a cylindrical coordinate, versus the moment reaction. So this is what you see on the chart. So that's the buckling torque or moment, and this is the post-buckled behavior. If you want to see a comparison of linear eigenvalue buckling with the nonlinear buckling, you can see it on this chart. Here's an animation of how the buckling progresses. Finally, let's look at an example of flexural buckling. So I'm just going to open this model. Here I have a beam fixed at this end and a unit displacement is applied at this end. The goal of this problem is to find the buckling load capacity of this beam. Here are the boundary conditions fixed at this end, and remote displacement is applied here. As you can see, I'm applying a unit 1 millimeter displacement in the y direction. If you look at the eigen buckling modes, the first 3 modes are very close to each other. So basically what it says is this beam is going to buckle at 35 millimeters of displacement in the first mode, and then at 38, and then at close to 39 millimeters. So if you look at the buckled mode shapes, this is mode 1. It sort of looks like a global buckling of the beam as it's bent up. Mode 2 is more like a local buckling. Mode 3, mode 4, and as we go to higher modes, these waves are just going to multiply. In problems where modes are very close to each other in magnitude, what I've found is that when I do the nonlinear buckling analysis, mode 3 might happen before mode 1, or they may happen simultaneously. So we will see how this goes when we do the nonlinear analysis. Let me just move on to step 3 here. So for the nonlinear analysis, I'm importing mode 1 buckled shape at a scale factor of 1. It's not clear which mode we should bring in because the modes are very close to each other, but I'm starting with 1, and let's see how this thing progresses. So I'm just going to open this model here. The nonlinear model has identical boundary conditions, as you can see here. In the remote displacement, instead of 1 millimeter, I'm applying 100 millimeters. So if you recall, the first buckled buckling mode was at 35 millimeters displacement. So I'm applying 100 millimeters so I can go past the initial buckling and look at post-buckle behavior. We might be able to see mode 2 and mode 3 also happening. The material is bilinear steel 355. Here's a look at the bilinear model. Here are my analysis settings, the sub-steps, large deflection on. The force convergence looks pretty good. This is the point where, as you can see, buckling happened and then something else happened here, you know. So let me show you how the structure buckles. So if I play this, you can see that this was mode 1 and it almost happened simultaneously with mode 2, which was bending of the membrane here. You can also see a slight amount of local buckling at this end. So let me just put it like this. So you can see this local buckling. So the entire beam, as it's bent up, sort of twists at one end and then proceeds on with local buckling at the flanges. If you look at the load versus displacement chart, so here the moment is plotted at the root. So when I'm applying this force, there's going to be a bending moment along the mx direction. So that's what I'm plotting. And on the horizontal axis, I have the deflection of the beam along the y-axis. Here is where we buckled, and then there is a secondary buckling. You can see the two waves here, and after that the load bearing capacity of the beam just drops significantly, unlike the previous charts of shear buckling, where if you recall, we still had a significantly high post-buckled load bearing capacity. So this is going down as I'm applying more and more displacement at this end. So this concludes this video on buckling analysis. I hope you are able to replicate some of these models and you are able to simulate it the way I've shown you. If you have better ideas, please do let me know in the comments. And if you have any questions or anything, please do let me know. Thank you so much.